This is the project presentation for course project EL6512, Image Processing and Computer Vision. The project name is Implementation of Sobel Edge Detection on FPGA. My name is Ruyi Zhang, and my UFID is 21728964. My email address is zhangrui1993@ufl.edu. This project is a course project, like I said before. And why do I do this project? This is an implementation of Sobel edge detection algorithm. First of all, image processing is a technology that process image to satisfy all visual and other needs of peoples. It is really important in the fundamental application in image area. For most of the image application nowadays, we do it in a digital way, and actually image processing is one of the branch of the signal processing, which usually to be one dimension, and image processing is two-dimensional. For this project, I chose edge detection as a specific image processing function to implement, because edge is the place that we store most the information. If the picture is whole black or pure white, it doesn't contain much information unless it has like a sharp change in light or color. For this implementation, I'm gonna only use grayscale picture image for this project. And also, I chose to use FPGA field programmable gate array as the tool for this implementation, because we all know that the algorithm itself can be really simplified into a formula, but the FPGA make it more complicated to implement it in the hardware, the board, and because you have to think about time and pipeline and hardware, all that stuff, it make it more complicated and more challenging. And also the FPGA's parallel is faster than normal software implementation as well. Okay, now we can see like this is an example for Sobel edge detection. Yes, here's the example. For Sobel edge detection, why do we choose it? It can tap the maximum parallelism out of FPGA as compared to the microprocessor. It plays a very important role in various applications which requires extraction of structural features of an image. Okay, here's the edge detection algorithm. You can see this is a mask, and this is the original picture. If you were convolution the mask into the picture, about that, like we said, image processing is a lot like signal processing. The difference is like image processing is two-dimensional, so whatever processing we're doing to the image, it is you're doing the convolution calculation to the image. And this is the specific edge detection algorithm we're implementing in this project. And this is a mask, like I said before, and this is the original picture, and this is the formula we use. Okay, and this is the convolution formula, and after introducing the algorithm, we can head to the design and implementation. This is the overall architecture design for the program. I'm gonna tell you some detail about this architecture. The main function and there are 3 BRAMs. They're used to connect to the map. The memory map is the memory where we store all the data, and connected to it's working like a cache. Like you put data from memory to RAM, and it goes through smart buffer because there are some data weight difference from RAM and the data path. So we need smart buffers to transfer that to cover that change. And we store the output into VRAM and put it back into the memory map. We use address generator to control like which data to write into VRAM and which data to write from VRAM to the memory. And the glue logic is to get the memory map and all the signals, control signal from the software into the controller, connect those. And the controller is where we control the pipeline of the data path and how data goes in and goes out, and control all the enable signals and the controlling signals. They all do it on the controller. And data path is where we implement the algorithm, the main logic of the algorithm. We can see it in a detailed way, and this is how should BRAM look like, because we store different lines into the BRAM. Because, for example, in BRAM 1 we store line 1 to line 126, and for BRAM 2 we store 2 to 127. For BRAM 3 we store 3 to the 128. We did that because we need different data, like we said before in the convolutional, we need this straight lines, so we have to put different data into 3 BRAMs and put it into data paths, so I won't worry about it. Yeah. And here's how we transfer data from BRAM to smart buffer. The BRAM data is the width is 32 bits per BRAM, and the data paths require 64 bits instead. So we have to deal with that using smart buffer. And here's the data path design, and you can see we put the data from buffer and put it into the data path, and the data path will process it. Basically, the data path do this work, like how we each implement the formula, and the controller control how data path runs and the pipeline and everything. And so the most important part is design of the controller. This is a controller. It has 1, 2, 3, 4, 5 states. You can see it like the control signal. When go is 0, it go back to idle. When it's 1, it go to start, and the next cycle it go to cold, and next he go to load until he will wait until the valid out is 1, and it will output the data. And when the output address is equal to like whatever you want, it goes to results and start writing the results. And after writing the result, it goes back to idle. This is the whole state machine. It is actually it is basically a state machine. And now we can see the result. This is the result from MATLAB. And here's the result from like the data path, how it should be output, like from the data path alone. Without the pipelining, it's just one data and one result. And this is the input is 1, 2, 4, and the output data should all be zeros, and it is correct. And this is another dataset test on data path. The inputs are 128, 129, and 8. The output of the last 2 bytes should be all ones, and it is correct as well. And this is a whole simulation from Vivado to this is correct as well. And because of limit of time, I didn't get to the board result to resolve into picture. It's only the decimal data. And here's the speed up. And this is a comparison of this is the original picture. This is the MATLAB social badge detection picture, and this is my output. And here's the difference. Okay, so much for the project. I will do a demo for now. This is the problem I solved during the process.